G'day everyone, Glenn Morris here from the Smart Energy Lab, presenting a very special Toolbox Tech Talk. Now, I've got the whole team from the Yarra Energy Foundation that I had the privilege of working with on a project recently, and we thought we'd explore this project with you. It really helps understand what microgrids are, the different types, and we dived really deep into this, and we have got the client as well, or a representative of the community as part of this team. So let me introduce Chris Wallen from the Yarra Energy Foundation.
Hello, Glenn.
G'day, Chris.
Thank you for having me on this program. Great topic today. So I work for Yarra Energy Foundation. We're a not-for-profit. We've been around for about 15 years. In more recent times, we have been working on community batteries. And you can see part of one of them behind me here, which is our first one in Fitzroy North in Melbourne. We're based in Melbourne. And community batteries was a way for Yarra Energy Foundation, or YEF as we call ourselves, to get into the battery storage space at the mid-scale level. This actually took us into battery backup systems for sites that could also provide community benefits, not only in terms of resilience, for example, but also by generating revenue. And that actually took us to the next step, which was we received a very intriguing request for proposal from Trentham Sustainability Group, Trentham being a town in Victoria. Does that give you an idea, Glenn, of where we started off from?
Yes, and I had the privilege of actually going to Trentham and walking around the town and trying to count the number of roofs and finding out where the transformer was. Yeah, it was a real world problem.
Yeah, and it was really interesting because it was we had to back up the center of town. And so a lot was to try and figure out what is the center of town and what is in it and what is not, basically what's connected to one particular transformer or distribution substation, and everything that had to unfold from that. So I think many towns, whether in Victoria or elsewhere in Australia, would have similar thoughts of, how do we deal with climate change and build more resilience? So this was like a textbook case, as we saw it, of how to dive into what does a town do to keep power on when storms and other things happen.
Yeah, well, I guess we should hear from Joe.
Great. Hi there, Chris, and hi there, Glenn. Great to see you. Yes, I am a member of Trentham Sustainability Group. I moved to Trentham, or nearby to Trentham, in 2023, and I'm also a core project team member for our Energy Resilient Trentham project, which is what we're talking about today. So first of all, a bit about Trentham. Trentham's 100 kilometres northwest of Melbourne, the capital city of Victoria. We're at an elevation of around 750 metres and we're exposed to extreme southerly winds. They typically feel like they're from the Antarctic. The township's surrounded by tall forests, tall messmate, tall grey gums. It's an amazing, beautiful forest. The township's at the end of a single feeder electricity line, and similar to surrounding districts, which are at the end of other lines. So it's got a very fragile energy network bringing electricity to it. So in June 2021, there was an extreme windstorm. People say that it was like having a 767 over their house for 12 hours. It was a big windstorm and had a devastating effect on people's hearts and on the physical nature of what happened around the town. Large swathes of the Wombat Forest blew over. It was like pickup sticks. Many trees fell on the grid power lines around Trentham, on the feeder line coming into Trentham and in the surrounding districts. And of course, in Victoria, the network infrastructure is ageing. It's now about 60 years old with a lifetime of about 70 years. So we're talking about really ageing infrastructure. Trentham was without electricity, without communication, and it was without water for at least 3 days. Surrounding districts had outages that extended to 7 days or even up to 3 weeks for some locations. So it was a pretty devastating experience. And because of the forest, you couldn't necessarily, and the trees on the ground, you couldn't actually get access to the town to bring in supplies or to bring in energy solutions. People had a really difficult time. I wasn't there, so I'm telling the stories that others have told me. At the supermarkets, the food was lost from the fridge and frozen goods. The hospitality businesses lost their food and their storage. You couldn't access the pharmacy for medications. You couldn't go to the bank for money. The pub was closed. It was midwinter. It was the 21st of June, midwinter, extremely cold because Trentham's cold on the very best of days. So this whole event raised many questions about household energy resilience, about community energy resilience, and about network energy resilience. So some very enthusiastic members of Trentham's sustainability group, and I will mention Sebastian Klein here because he was key to this, starting it all off. The rest of us are newcomers. We got busy. We applied for grants, and in 2022, we commissioned a scoping study on what some of the solutions could be to get community energy resilience so that people could not just have energy to their households, but access those important things that communities need to stay functioning. That initial study reported in 2022, October, and it recommended a microgrid as the best solution, a low voltage islandable microgrid. Following that study, we applied for various funds so we could then go into developing a technical feasibility study in greater depth and to do a business plan. And this all came together finally in early 2025 when we found Yarra Energy Foundation and SolarQuip to do this study for us. And this is the story of that journey. Thanks, Glenn. Thanks, Chris.
Wow. That was a pretty awesome response to a critical situation, which is how do we fix this properly? And that's kind of where Yarra Energy Foundation got connected, I guess, Chris. So what about the design of that project? Shall we bring in Finn to talk a bit about that?
I think as Finn comes in, I think the context for us was that we were looking at that and needing to bring some expertise in the microgrid space. And who could be a better choice than Glenn Morris when it comes to microgrids? So I made a call to Glenn. I know Glenn, have known Glenn for quite a while. He was a lecturer in one of my classes a long time ago. And he was ready to go for it. So we thought, all right, let's get together, SolarQuip and YEF, Yarra Energy Foundation, and see what we can do. And of course, that's how we brought in Finn into the picture, who is a master orchestrator of the many projects we work on.
Oh, thank you, Chris and Glenn and Joe as well. I got a whole new wave of excitement for the project listening to Joe talk through the history of it and the context. And I think that was kind of what hit me when the opportunity first came across the desk. Just how much of a need there was, and also it was really clear, always been really clear, how much work and TSG has put into developing this project. And there was a lot of history there to get a hold of. And I think initially that was kind of the first big challenge of this project, was just to understand the huge amount of work that had gotten it to this stage, where TSG had arrived on a really quite a clear concept, I think, of what they wanted the solution to look like, and what a solution that would meet their resilience needs. And I think internally in YEF as well, I think we instantly kind of recognized that while Trentham's a brilliant example of this need, it's also something that, again, I think applies in a lot of similar townships, both in Victoria, nationally, internationally, in the context of a changing climate. Energy resilience is just going to become, I expect, a more and more pressing topic. So for us, it was immediately a really exciting study to get to have a look at. And I think after a bit of back and forth with TSG, we arrived at a pretty clear scope for the study itself. And that kind of being these 4 points in front of you now. Initially around really this assessing the technical feasibility of whether a grid-connected microgrid in Trentham's context that did have some of these key metrics. It was identified what transformer, and that was a key central part of Trentham that provided power to some of the key businesses and would provide a central location for everyone to come to in the case of an event. There were 66 residential homes in that area and 36 businesses. And the intent or the goal was to design a system that could back up that area for 4 hours on the battery alone, but then also allow for longer term backup, and that being up to 3 to 5 days by having a portable diesel generator or a diesel generator installed alongside the battery that could kick in when it was more of an extended outage and a larger event. And part of that as well, an overlay for TSG that was clear in their RFT was that the actual sustainability and the environmental credentials of the solution as well was something that was really important. It wasn't just bringing in a big diesel generator and having dirty power, so to speak, but rather trying to do this in a way that could also reduce the emissions and the environmental impact of that local generation as well. So to assess that technical feasibility, we were going to need to build up a microgrid design and not only the hardware, but then also software and operationally as well, with TSG being a community group, who would actually own these systems and run them, and who could we partner with to make that affordable and achievable in this context. Once we had that design, we were tasked then with that building up a financial and commercial analysis of how the project could make sense, and could we get a return on investment that would allow the project to go ahead to make it financially feasible. And so the fourth point there, also having a second overlay of, as we're moving forwards in the energy transition and we're seeing more localized generation, we're seeing changing load profiles in our networks, how could we future-proof the project and future-proof any design to account for things like increased EV charging, increased electrification, possible future vehicle to grid? So could we even consider a way to maybe bring in that as an additional source of resilience in a time of need? With some really kind of big picture, exciting concepts as well to consider as part of the study. And to practically deliver on that, we stepped it out in 5 steps. So the first being actually looking at the network that we'd been asked to back up to understand what's the load looking like, what's the generation like, what are the technical parameters, and how much, what does resilience actually mean in the context of this project? The second was, once we had an idea of what we were backing up, was to actually figure out how we'd do it. And so that was designing the microgrid equipment and the systems that would enable us to provide backup power in times of need. And then it came to actually modeling that design, looking at across 10, 15 years of operations, and not only having it as a resilient system, but also a system that could generate some financial benefits in the energy markets. Trying to find ways that we could utilize the assets as much as possible to not only provide that backup power, but to kind of wash their own face in the market, so to speak. And the fourth was looking at that across the 10 or the 15 years of operation. So what's the system earning? What are the costs? Where do we end up after 15 years? And is that a financially sustainable project that can be taken to the funding stage? And the fifth there was buttoning all that up. And again, I think initially the intent was that we could try and get the project to a point where TSG could carry it forwards to a funding application. And as part of it as well, looking at exploring possible partnerships for them to carry forwards, possible funding streams through relevant government programs, or even potentially some private involvement in this kind of project. So it really was the kind of complete feasibility and beginnings of a business case development work, which was really exciting and a great learning opportunity. And I think having Glenn there as well as the guru on all things microgrids was a really great opportunity for us. But I think kind of where it all started, and I guess, back to you, Glenn, I think the first thing was around that network data and what is resilience? What are we actually having to back up, and what does the Market Street low voltage network actually look like in practicality?
Cool. Well, I think we should introduce Farney at this point, because this is where Farney really got strongly involved. G'day, Farney. So tell us a bit about, defining what a microgrid is and maybe highlight some of the insights.
I think this project was particularly interesting for us because this was the first foray for YEF into the microgrid space. Previously, we worked on the front of meter installation, slowly getting into the behind the meter backup and resilience space. But the scale of the project, so looking at 100 properties to back up, was something that was new for us. So I think we initially started around with some research on what is being done around in Australia. And very quickly, we found that microgrid was a term that was used to refer all sorts of things and many things. And broadly, microgrid, you can think of it as a small subset of the main electricity grid, which can operate independently during times of outages. But this definition was very loosely being applied to many different systems, many different operational contexts, etc. So when we looked to narrow down on what was there in Australia, we found there was two main types of microgrids that are out there. The first being the grid-connected microgrid systems, and the other being off-grid or standalone power systems. And the main difference being, as the name suggests, the grid connected ones are typically connected to the main electricity grid, and they only go into a microgrid mode when there's a power outage. And this is particularly the context that we were looking for Trentham. So we want to be connected into the main electricity grid, but whenever there's an extreme weather event, Trentham wanted to have the capability to operate independently of the main grid for that particular period when it's needed. And when looking at off-grid systems as well, I think, Glenn, you're a particular expert on this. The Mura cooperative operates on an off-grid standalone system. So it's a very different type of microgrid, which comes with, of course, different challenges. So first thing was we delineated what we're working on, and we pinned it down that we're working on a third-party owned microgrid system. So we are not, again, a DNSP owned system, not owned by a distributor, which comes with different set of requirements, whereas we will be a third party owned system. And I think the first step, as Finn was mentioning, was starting to look at the network data for a particular transformer in Trentham. So the transformer was called the Market Street transformer. It was supplying roughly 66 houses and 36 businesses, so quite a few properties there. And we received 30-minute interval data of consumption and generation from PowerCore, which was very helpful for us at the very beginning. When we started looking into the data, I think the first thing we did was segregating the consumption across the different seasons. So understanding how are the consumption profiles across different seasons, what's the daily average load that the transformer is supplying. What we found was the transformer was roughly supplying 3 to 4 megawatts hours of energy per day, which is quite a lot. And unsurprisingly as well, the winter consumption was quite high, so roughly touching that upper limit 4 megawatt hour mark on a daily basis. We also looked at peak demand, what was the maximum power demand on the transformer, and based on the 30-minute data that we had, we roughly estimated about 278 kilowatts of maximum demand, and the maximum generation as well we saw was about 100 kilowatts on that particular transformer. So when the sun is shining brightly, we can expect 100 kilowatts of power to be generated just within that area. And I think going well beyond this, we also looked at power quality data for that particular transformer. This is mainly around how the voltages are behaving on that transformer, and how much load is there on the each phase. So I think everyone is aware that nominal voltage is 230 volts in Australia, and what we found in the Trentham case was the voltages were higher than the nominal voltage on an average. So roughly, the voltages were hovering around 240 volts, which is typically higher than what you want. And the phases as well, the load distribution on all three phases were not even. I think one phase has a particularly high load, and the other two, maybe because of higher solar generation on them, had a quietly lower load levels on them. So there was a particular load imbalance on the three phases in the network. Now, all of this might be okay when you're grid connected, but when you're going into off-grid mode, these are not things that are good to have. So you want stable voltage levels, load balanced across three phases. Then we had to go and really think about, okay, how do we design a microgrid that can effectively supply power back to all these residential and commercial businesses during time of an outage. And I think that is when Chris led the part of that part of the design in this project.
Well, I think we'll bring Chris back. G'day, Chris.
Yeah, the design was tricky because first of all, we need to be clear on the fact that this is a feasibility study. It's not a procurement. And so we had to put together a high-level design, but we also had to cost it, which meant that we couldn't just come up with what we think looks good. We had to also find out what it might cost to build that and see what options we have. And so that meant, and I guess it's a common thing when you do feasibility studies, is you need to involve those people who are expert in the delivery of these systems to be able to get the numbers that you would use. So actually leaning a lot on Glenn and his contacts throughout the industry, and I can tell you he's got a lot of contacts, but also some of the contacts that we had, we requested some assistance in giving us an idea of how different types of equipment, what it might cost, the lead time issues, and from that we could come together with what we thought was a reasonable design for what we're setting out to do, with a confidence level that was high enough for us to actually put that into the modeling that was done for the economic analysis of the project. So what you see here is a stylized version of this network and the connection into the residential properties and businesses. The actual implementation involved the center of town, but then there was an interest of an area a bit further away that had a lot of space. They had a lot of roof space for solar, and there was a keen interest to connect that in. For simplicity, I will disregard that because there were complexities in trying to connecting another part of the network into this low voltage network, the Market Street transformer one, which you can see there on the pole. It was a pole top transformer connected to the grid. So what we needed first of all was a changeover switch, and that's in the switchboard where we detect whether there is still grid power or not. And if there is not, then we move into another mode where we source from other sources the supply of energy. So what does that mean? Well, you would have battery there, you would have a diesel genset there, you would have also solar, and we were looking at how much solar we could install on rooftops or even on the ground or on top of the equipment that we would be installing. There was a toilet block there we took advantage of as well, so that solar could actually replenish the battery during times of grid outage. The key here, of course, was the control system. And the control system has two elements to it. There is the normal supply case, which is where you do have the grid. In this case, you want a market participant, so an electricity market participant, to dispatch the battery in the most lucrative way, and if possible, together with any other batteries that are in the households. And then when we lose the grid, then that control system would have to optimize the flows of energy when we no longer can rely on the grid. So there's no market anymore. We just have to make sure that that battery system is operating in the best way possible, replenished by solar. And only when we see that we're falling down to a low storage level, state of charge, then we would need to get the generator in. There was no space there for a generator, so we were opting for a portable genset to be brought to site and connecting in, and then the battery would be supporting the diesel genset. So this is sort of the design that we had in mind, and so we went out to a number of parties. Some of them were very friendly and worked with us to give us some idea, but it was basically pulling it all together. And there was also the issue that Fani said earlier that, we needed network data, but we didn't actually get instantaneous power quality data. So that could not be provided by PowerCore. And therefore, we didn't actually know if the battery was going to be able to cope with very sharp, instantaneous peaks, and how that might vary through the day. And also, if there were particular offenders causing those peaks that might need to be load shed. Hence, there was this idea of, together with the control system, as I just described, there would also be a load shedding capability where certain loads would be disconnected remotely, automatically. So we were then trying to figure out, okay, we could probably source a battery system and we can probably source solar, but when it comes to the diesel genset, are there any options other than that? And when it comes to the load shedding, what could we do? Are there systems out there we could refer to? So what you do in this microgrid space when you don't know how to approach it, you go to Glenn. So therefore we said, hey, Glenn, here's sort of an idea of a design that we could use. How would you source different types of equipment that would allow us to do this, carry this out?
Thanks, Chris. So it was a very different experience for me, sort of being very much au fait with off-grid microgrids and understanding, the differences to a on-grid microgrid requiring some similar characteristics, which is independence from the grid when the grid fails. So initially, my first thought was, let's understand the loads, and that's kind of where we struck a lot of problems, understanding the loads. The information from the DNSP was basically just meter data at 30-minute intervals, and it's not quite enough resolution to really understand peak demand. Peak demand in an island situation became very critical for selection of equipment. It's all very well to know that the average sort of consumption is like 2 to 4 megawatt hours a day. That helps you size a battery system. And we were seeing some 30-minute loads of 280 kilowatts, but that's not a peak. That's sort of averaged over 30 minutes. And so when you've got a piece of equipment that actually has to deliver the real peak and it's going to have a hard limit, that's when we need much more accurate data. So we realized we probably needed to have some data logging to get that sort of information, and ideally like over a long period of time, possibly a year, to find those true. Otherwise, there might be an outage that happened to Trentham in the middle of winter, which is probably when some of the peaks occur because of heating loads. And then the system might not work because we modeled it for loads in the summer months. So that was one of the challenges. Also, the very spread out nature of the project. So, there's homes with some has solar. There's a location where we could put a battery next to a toilet block, but there was no room for solar next to it for a sort of ground mount system. We'd have to put that somewhere else. There was a high voltage interconnect between two parts of the network, which we're even looked into seeing how we might be able to utilize that. But we kept on coming up with a barrier that it's not our asset, it's the asset of the DNSP. And to try and get their cooperation on that would be quite difficult because you're really taking charge of their customers whenever the system islands, and they are responsible for the reliability of power to their customers, even when it's not reliable. So, that for me was one of the big challenges, understanding those differences, and also looking for opportunities such as demand control. So it's having appliances that you can control when they use power. Now, there's not a lot of things you can do that with, but resistive hot water is an easy one. And people would hardly even notice if their hot water system was turned off for 10 or 20 minutes as a peak was to flow through when they're in island mode. So we looked at the option of utilizing some retrofitting of hot water controllers to some of the residences, and also looking at expanding the amount of renewables. So having, particularly on quite a few of the businesses which had more sizable roofs, adding more renewables to the mix. So, there was a lot, excuse the pun, a lot of balls in the air that we had to try and juggle and see how that could land into a cohesive design. So, that's kind of my experience.
To talk a bit about the diesel genset and the challenges that it caused the project, because you may not use it all the time. On top of that, you heard Joe say before that when there's a storm, there may be a tree over the road, and so do you remember, Glenn, how we were trying to figure out what could be a good future solution for that? Have not thinking that for now, gensets are probably the only way, but we wanted to future-proof this as well.
Yeah. So, for the fairly rare occurrence of total loss of power, I know it's bad when it happens, but it doesn't happen every day. A genset is a sunk asset. It's a lot of money. There's maintenance ongoing, even if you're not using it. Things like making sure the fuel is still usable because, fuel ages. There's contamination problems with moisture and also so-called diesel bug that can grow in fuel these days because the removal of sulfur from diesel, which is good for the environment, but it's also good for those bugs. So you'd end up with something that you had to look after and nurse along on the off chance that you might need it. And of course, when you did get to use it, it is a non-renewable resource. It's rather expensive to run. It's very noisy. Can be put in a soundproof cover, of course. You've got to find a location for it. So we tried to think out of the box a little bit, like what else could we use that could provide a service similar to a diesel genset. There was, tossing around the idea of not having a permanent diesel genset that would get away from the maintenance issues and just having one that could be called on demand. So like a contract with a diesel company to supply within a certain number of hours. But that still led to some problems, like how reliable would that service actually be in practice. And then we looked at something that I saw in China, which was basically a battery-powered, or a truck with a megawatt hour of batteries and a half a megawatt of AC power that could just drive up and plug in. There's, to my knowledge, none such products in Australia at the moment, but it really started to look like something feasible for emergency power as a replacement for a diesel genset.
Yeah, and I think that really prompted us to having sort of got all the main elements of what we needed to complete the design, and getting costings that we had a high enough confidence level that would be representative of what the project might cost at the time it would actually go into implementation, which was a couple of years down the road from the feasibility study. And to be able to model this, then Fani took on the role of inputting all this information and both assessing the revenue that could be generated from operating the batteries on a VPP potentially, but also the costs involved and what returns there might be on that investment. Maybe we could bring or ask Fani to give us some perspective on that.
Yes. So we did go out to a couple of EPCs, engineering, procurement, and construction companies, to cost our design. So it included a number of elements that I think both Chris and Glenn mentioned. Diesel generator, a large BESS. So we were actually looking at a 1 megawatt hour BESS that could provide backup power for up to 4 hours. And we sized it up to 300 kilowatts of power. So this is based on the best available data that we had from PowerCore of the 30 minutes, roughly 300 kilowatts of max demand capability. And then we also wanted to include some solar in there so that the battery can recharge if the power is out for longer. So we included about 88 kilowatts of solar and load management software to turn off things like hot water systems, etc. So this mainly formed the equipment part of the design, and it roughly costed to $1.2 million from two different quotes from the EPCs. So that was the equipment part of it, but there are also other costs. Like we actually looked at a few sites where we could actually put the equipment in, and the best site that we thought was right next to that transformer in Trentham, which we were looking at. And we estimated that in order to put this equipment in, we may need to procure that land, and estimated a cost of $500,000 for that, and other costs such as project management, regulatory compliance, contingency, etc. All of this added up to a total price tag of $2.6 million in capex for the project, which is not small, but also not quite large as what we would have expected. And after this, we look to understand the operating expenses, things like administration of this microgrid. Even though it only is required, for example, a few days in a year, someone would still need to look after the equipment, maintain it, monitor it, etc. And the element of market trading. So except for the diesel generator, the solar, the battery can participate in the market to generate revenue when there is no power outage on the grid. So accounting all of that, we've estimated about $45,000 per year in operating expenses. And when we used all of this information to model future revenues for the microgrid system, again, we used a number of sophisticated inputs such as market price forecast for the next 10 to 20 years, and used all of that input all of that into a software algorithm, and we've estimated revenues of up to $362,000 over the 15-year period of the project life. So it roughly calculates to about $30,000 per year, but also a maximum of $42,000 per year. So these are some of the rough revenue that we expected from the operation of the microgrid. But that is just revenue. So in order to calculate profit or earnings, we have to take out the operating expenses. And when we did that, we actually went into a negative in profits over the 15-year period. if we take out the OPEX, we were running at a loss of roughly $300,000. So I think, and this is while assuming that the entire capex would be funded by a government grant, either from ARENA or others that are available. So it really made it clear that the financial viability of the microgrid is difficult, especially if the cost of equipment doesn't come down, or if some other factors do not change in this capex equation. And I wanted to also highlight the two main reasons of why we think the microgrid did not have a positive business case. And again, the first being the high capex of the microgrid, not just the equipment, but all the other aspects of it. The cost of implementing such a complex project has an initial upfront cost tag, so that is something that would need to come down in order to make such a project viable. The revenue again is comparatively low to the amount when compared with the capex that we're putting in. And I think one of the interesting insights as well that we found was when, for example, a distributor puts in such a microgrid, it is possible for them to justify such an investment by calculating the value that they provide to the network. So there are these figures such as value of network reliability, value of customer resilience, etc., that are published by the Australian Energy Regulator, which DNSPs can use to justify their investment. So for example, if Trentham has 100 hours of outage in a year, there's a certain value that is set for that each hour. So could be $1,000 an hour, or even more than that. So DNSPs have access to such a value stream to justify their investments to the into the network, whereas us or Trentham, being a third party owner that wanted to implement a microgrid, does not have access to a similar revenue stream. So which really took out that option when we make a business case, for example, to a funder. So those are the couple of main reasons that led to a negative financial business case on the project.
I think, needless to say, that we were disappointed that we were not able to make it a positive business case, because that's what Jo and her colleagues were looking for. And I remember us going back and forth on this and trying to really drill down on, well, what is it that's costing us so much? Why can't we break a profit? And it came down to these operating costs that could not be brought down sufficiently to be lower than the revenue that was generated. And finally, I believe we looked at different ways that we could look at these operating costs. What are some of the sort of barriers we just could not overcome in terms of bringing those costs down?
I think from a capex perspective, the cost per kilowatt hour of the batteries is coming down substantially, but still high, which we couldn't bring down at current market position values. And the cost and complexity of implementing this project, we did want to have healthy contingency budgets when we're going for such a complex project. It is very possible that the costs can expand depending on the complexity. So we did not compromise on any of the contingency that we would have to cater for. And when it comes to operating expenses, I think the standard operating expenses for the battery, solar, all remains, but a key operating expense was the diesel generator. So I think even though it may be used, as Glenn was mentioning, very little during a year, it would still need to be maintained. The fuel needs to be maintained, and we also need to make sure there's enough fuel to supply during an outage. So it's not like we can leave the diesel generator without any fuel in there. which I think which essentially led to OPEX being high as well. So out of the $45,000 in operating expenses, roughly a 20,000 of that was going towards the diesel generator itself, and we were accounting for 100 hours of backup. So we would have enough fuel in there to provide backup to the town or to the microgrid area for up to 100 hours, and these were costs that we just couldn't take out from our capex and opex equation.
It was hard to make the assumption that that would be a shared genset in the council and somebody else would pay for it all, because, again, when a storm hits or a bushfire hits and all the roads are cut off, well, that's it. You're not getting a diesel genset. So we're going to have it locally, which means that we had to have those expenses included. So
maybe I should bring Joe back just so we can have a general discussion at this point. So welcome back, Joe.
Hi, guys.
Hi. Yeah, so Joe, what was the feeling from TSG, at the end of this project?
It's a really good question, Glenn. And first of all, just casting back a little bit to what we had been led to believe in, and I think it was mid-2024, PowerCore, the distribution network service provider, or DNSP, as you guys are saying, had actually put into their plan for resilience that they saw Trentham as the highest priority for installing a microgrid. So PowerCore had actually committed to this in a plan, or I think maybe it was in a media article, and then later on they pulled back on that commitment to doing this. So the key point out of all of this is not having the distribution network service provider on board to actually support this and to be, perhaps even resistant was a big challenge of this work. So I guess we had hoped for a positive business case, but we also, another comment too on the economic modelling is that it hadn't factored in a beneficiary contribution. And so since we received the report, we've been thinking about how we could garner support for beneficiary contributions. And when you look at the what it might cost someone, it might cost to a household only $200 extra a year to buy that resilience. And we were thinking about a subscription model. So we haven't advanced far along that, and we haven't yet put it to the community. But we are sort of working on some next steps. Another really important thing that has happened in Trentham in the meantime is that Trentham successfully gained investment from the Victorian government, one of 10 townships in the region for a neighbourhood battery funded by the Department of Energy, Environment and Climate Action on the community centre. But that'll be a behind the meter, I think that's the right term, battery, 280 kilowatt hours, which will only provide a resilience for that actual building. So that was an additional battery, which will happen over the next year or two, as well as additional solar on that building too. I guess we realised that our community is not alone, and Finn had mentioned that earlier. And we also started to think more deeply about household resilience in energy and what community energy resilience is, which is exactly this part of the picture versus network energy resilience. PowerCore came back to us and they had said they were keen to do to strengthen one of the feeder lines or put in an additional joining up piece. I don't remember the technical things, but it was a solution that still would not have worked on that day when trees were over power lines everywhere. I'll pause there. Yeah.
Now, in the report, we did suggest the alternative that I think the capex was about $2.6 million. If you had access to that amount of money, the alternative could be to provide homes and businesses with backup systems.
Yeah.
So that while you cannot provide it for the whole center, each individual one could actually have their own. Now, you may not be able to achieve the 3 to 5 days autonomy that you were seeking, but at least it might cut out all those relatively short duration outages that I believe Trentham is regularly having to experience. So not the ultimate solution, but possibly an intermediate solution. And what motivated us to look at that as an alternative was the federal rebate on home batteries that I guess now we know has been very successful, and that could be a way to at least mitigate the predicament that Trentham ends up in very often.
Yeah.
Yeah, another benefit that was, I think, as we were exploring that, Chris, that was really clear was just being able to also remove the complexity that I think Glenn touched on earlier around with islanding a whole low voltage network that we would be supplying customers in a network provider's area, and a whole lot of regulatory challenges there that would need to be worked through, and a lot of safety considerations. And I think it was actually something that probably sat outside of the budgeting that we did, because we couldn't really put a figure on it, was the actual work that would need to be done with the network to figure out how it would integrate into their systems and how it could be safely deployed. And also, from a regulator standpoint, having a third party providing that backup service to a part of the regulated energy network, how would that work and what rules would apply? Yeah. So by moving it behind the meter, it was, I think, in the immediate term, while those questions are being worked on in the background and are still, hopefully will be answered in due course, it was an immediate step that could be taken, and one that I think TSG has taken with the neighbourhood battery, behind the meter neighbourhood battery project at a key site there in the town as well.
Mm. Now, there was an interesting point, excuse me, Glenn, related to that, which is PowerCore would benefit from a third party implementing this microgrid in that it reduces the unserved energy. So there is a clear benefit here to PowerCore by a third party stepping up and doing this kind of thing. So we approached PowerCore on this and said, do you acknowledge that you get a benefit if a third party was to do something like this? And they said, yes, we do. Clearly, if you do this, then it serves our purpose. And they were ready to contribute in some way towards that. To be defined, because I don't believe there's any precedent of this. But at least it showed that there is an interest there for them, for someone like TSG to go ahead with a project like this. But there's a lot of open questions also, as Finn just said. So suddenly we are in island mode. Well, and a third party is making sure that the poles and wires are working well. So yeah, a lot of regulatory issues when you cut off from the grid, not because you want to, but because the grid is no longer supplying.
Yeah. We have reapproached PowerCore since, and they basically said, no, thank you. So since the study was released, they're definitely not interested. So it's a bit disappointing. So we're reverting back to some other thinking around supporting businesses to install changeover switches and purchase their own generators. And that's had some success in another similar area in South Gippsland. Yeah, it's sort of not the whole beautiful solution, but it's a part of the community energy resilience solution. But then you strike the interesting space of the issues of most businesses in Trentham are actually tenants. They don't own the building. So you've got this landlord-tenant arrangement for, who owns the energy infrastructure and who needs to use it and who needs to own it. So many, many challenging ideas to explore.
And there's probably also this unknown of the vehicle to home, vehicle to building, vehicle to grids opportunity, and how that's going to play out, what the uptake is going to be, and what is the time frame for that. So, but it does show that if you go down that alternative approach, there is probably more opportunities along the road of how you could make each installation more autonomous, more resilient.
Yeah.
Actually, Chris, I was just musing about the word resilience and the different levels that you can consider resilience. I suppose at the simplest level, something like a UPS for your computer provides you with resilience for just communication and maybe work. A home battery system with backup or a changeover switch with a portable generator provides you with resilience at a home level. But once you go beyond that, then you have to work with third parties such as DNSPs, trying to provide resilience at a transformer level. And those, in a way, have some weaknesses as well, which is you still are very reliant on that one system for many, many people. So with the advent of a couple of financial incentives, like the cheaper home battery program to make batteries very cheap, and maybe some other funding sources, it means that you could bring that resilience down to a home level. But you do raise a good point there, Joe, that it's the renters that miss out. 30% of Australians rent. So there's a lot of people who miss out on sort of government programs that encourage the uptake of solar and or storage. So we still need solutions for 30% of Australians, and plus all those businesses which are renters as well.
Yeah.
I agree. The renters tend to always miss out on these kinds of things, and I think that's where the strength of the community has to come through, of how do we actually provide the services to the community in times of outage, overcoming this landlord-tenant issue. And it's not an easy one. I mean, beyond microgrids, it's something that happens everywhere in industry and commerce, of how can you actually got warehouses with huge roofs, but there's no solar on it, which makes no sense. Businesses consume in the middle of the day, and you're stuck in this triad of how do you make this work?
I can provide some positive or silver lining to the microgrid study that we did as well. Following the development of the study, we also had a chance to meet with the AER and AEMO, where we've explained what we've done and the challenges that we see, or the obstacles and the barriers that we see to implement a third-party microgrid installation. And I think there is a clear understanding within the regulator and the market operator that these sort of solutions are not far away. So they're very close, and steps are being taken slowly, but they are being taken in the background to enable microgrid operations into the future. So I think we've got some examples, such as in 2015, AEMO proposed a change to have standalone power systems which are not connected to the main grid, but for rural remote communities, it's much more efficient to build an independent standalone power systems. You see a lot of these in Western Australia, and those have been approved and rule changes have been made. The next step that they were taking was unregulated SAPs, which are standalone power systems. So for the main electricity grid, there are a number of rules and regulations that DNSPs need to follow. But SAPs, if you put the same obligations on them, suddenly become prohibitive from an administrative and cost point. So AEMO and others were looking at introducing rule changes that allow unregulated SAPs to operate. Maybe Glenn, the installation at Muramura would come under an unregulated standalone power system there. And lastly, they were looking at the temporary SAPs. A power system, let's say that is a Market Street transformer in Trentham, that can be temporarily disconnected, but again connected back into the grid. So, I think they clearly see that if someone doesn't drive the outcomes, the technology will drive them anyway. And there's a clear need that was identified that communities need to lobby and show interest in this solution to make these changes happen. So that was, I think, a key learning as well, following from the project that we did.
I think that's great that they see it this way. I think the question that's on my mind is, at the moment, the only ones that can financially justify a microgrid is the electricity distributors, the DNSPs, the way our study showed. So taking what you said there, I'm wondering if that means that the distributors will be given more and more latitude to deploy microgrids because they can actually make that work financially. It means that all of us will be paying for, through our tariffs, the deployment of these microgrids by the distributors. Or will there be a way that third-party owned ones can actually come into this marketplace, be able to play a role?
Yeah, they're really interesting ideas, Chris. Yeah, and yeah.
Sorry to interrupt, but we are sort of coming to the top of the hour, and it's been a really great discussion. I mean, I've been kind of part of this project, but it's just great to introduce the whole team here to my audience. But look, I think we should also plug the fact that this is going to be a presentation at All Energy. Finn, I think we're going to be giving it.
Yeah, definitely, and diving into, I guess, some of the control sides of it as well. So yeah, I think it's on the second day, final session in the afternoon there. So it should all be in the program under YEF's TSG Trentham Microgrid study, which will be really exciting.
So they've put the best to last. Yep.
It's all up at All Energy for sure.
Yeah.
Okay. Well, thanks very much for coming along, everyone. Joe? Oh, yes.
Can I thank some sponsors, the people who funded this study? Is that okay?
Yes.
Yeah. Well, I'd like to thank Hepburn Shire Council, who contributed, the Foundation for Regional and Rural Renewal, the ANZ Seeds for Life program, Cool Country Enterprises, that's the Trentham Community Bank. I'd like to thank Mycelia Renewables, who've supported our community engagement. And I'd like to thank Yarra Energy Foundation, who have contributed so much more to this project than we were able to pay for with our small grants. And SolarQuip, of course. Thanks, guys.
Great. Thank you, Joe. And I'll catch up everyone, or at least Finn, at All Energy. And it's 2 weeks away. So get your tickets. It's free, but, just so you don't have to queue up, you can do it all online. Anyway, thanks very much. Well, that was another special edition of Toolbox Tech Talk, talking about a topic really close to my heart, which is microgrids. I've built what I like to call the accidental microgrid here at Murramura Co-op. Really basically started off as a training system and then became connecting to some homes. And before you know it, we had a microgrid. So, it's very close to my heart. And effectively, I'm a little micro DNSP as well. Anyway, thanks for watching, everyone. I hope to see you back next Sunday at 1 o'clock Australian Eastern Daylight Saving Time. Or it might be, if we're lucky, DJ Glenmo. We might be able to get him back on to do some more live stuff, because his live last weekend was not live. He pressed the wrong button. God, he's a bit of a waste of space sometimes. Anyway, thanks, everyone. See ya.